So doors are shutting. Let's get started today. Thank you all for coming. I am Niraj, Tolia. I'm joined here by Julio, Lopez, my co-presenter. We are both from Kasten. We are a company that does a lot of things in terms of being data management and cloud native. A number of questions that came up in previous sessions around cross-cloud portability, around data protection for backup and restore stuff that we do. But we're not talking about any of that today, right? This is not a vendor talk. The goal behind this talk is, especially for those of you who might be new to Kubernetes, to show you how it is ready for running your stateful applications in there. We're going to focus on three things over the course of this talk in terms of what the platform supports to build out these applications, what storage vendor support is out there, as well as some of the higher level application concepts that is making it possible to run databases, NoSQL systems, things of that sort. We are not going to go into excruciating detail in this, but the goal is to have you walk away with a good sense of where to go look if you need more help, or also what to think about when you're building and deploying your applications in these environments. So I think at this point in time, most people in this room are familiar with what Kubernetes is. At the very high level, it's a container orchestration framework. It's won the container orchestration wars. It makes it much easier to have automated deployment, scaling, and management of your containerized applications. So, but in theory, to some people, this sounds boring, but there's a lot of excitement in the community around this today. And before we jump into stateful applications, it's good to think about from the first principles why people are so excited about this, what motivates them, why is Kubernetes succeeding where some of the other platforms did not. And in particular, a lot of it comes from the philosophy, right? The Google talk touched upon this a little bit, where the platform by itself is very developer and application focused. Right, it sometimes gives vendors short thrift, but it puts the need of people that need to move quickly first. That has led to a lot of success for it. It definitely enforces good DevOps hygiene, both with immutable containers, with the use of CI/CD pipelines, enforcing configuration as code to make it easier for you to manage and scale applications. And finally, it uses a declarative approach. If you're not familiar with this, it's simply, instead of telling the system to do something, you tell the system what you want the state of the world to be, and it tries to reconcile that. It's actually very powerful in reasoning about both distributed systems, as well as figuring out what's happening in there. From the development point of view, whether you're building a storage system like OpenEBS on this or applications on that, the number of advantages you get out of the box. I really wish I had this available to me in a few previous companies, because it would have saved me multiple man-years worth of effort in some of the projects I've led. So in particular for applications, it has a lot of self-healing properties. When nodes die, clusters die, it will help you bring things back up. There's auto-scaling in response to loads, so you can meet your performance targets. From the infrastructure perspective, administrators like that, much better resource utilization than virtualization-based environments, better bin packings happening here. Greater portability across multiple clouds, across multiple environments, because its goal is to insulate the developer from the underlying infrastructure there. And again, going back to the developer, when you have applications, large number of things that it provides, including graceful deployment options when you want to scale up, down, upgrade, when you want to do service discovery so you don't need to hard code stuff. So there's a lot of stuff that's gone into this that you can easily leverage in building your applications out there. But more than that, it's the power of community. This is the cloud native landscape that's been published by the Cloud Native Computing Foundation. And while not everything is a Kubernetes project, a lot of them do support Kubernetes. So when you get started on this, there's a lot of stuff out in the ecosystem there that's going to go help support you. Yep. So I'm going to next switch tracks a little bit and just talk about some of the high-level Kubernetes concepts that will be useful in the rest of this presentation. We're not going to go try to do an extensive coverage, but at the, as I said, high level, there's a Kubernetes cluster that is made up of nodes. Nodes can be a virtual machine, could be bare metal, really doesn't matter as far as things go. Some nodes are special. They're referred to as master nodes in these environments. This is where the API service sits. This is the node that runs scheduling for the rest of the system. You generally don't run workloads there, and they can be replicated for high availability purposes. Now, to deploy a new application in this environment, you simply tell the master node what you want. Right? You tell it, hey, I want this new app to come up. Here's a description, my resource footprint, the container IDs I want to go use, things of that nature. And based on that information, it'll go schedule it on some node that it might decide to choose. You don't know a priori. And this gives you a good sense of, right, at the very high level, how things work in the Kubernetes side of things. I'm going to rate at this point in time, unless there are questions, and please feel free to interrupt us with questions as things go along because we have plenty of time here. But I'm going to hand over to Julio, my co-presenter, my coworker, who's going to talk a little bit about some of the storage options there, and they'll come back and talk about some of the higher level concepts that you'll also find in the space.
All right. Thanks, Niraj. So as Niraj mentioned, Kubernetes gives us a very easy and flexible way to deploy containerized applications. So keep in mind that when we're running containerized applications, by default, the containers are not persistent, right? So a container always starts with a clean slate. This means that on-disk files will be deleted when the container or the pod restarts. Now, if we're running a stateful application, one of the requirements is to be able to store and persist the state across pod restarts or container restarts. So let's look at what options do we have to persist state in Kubernetes. Today, Kubernetes already has built-in support for persistent storage. It supports the storage from all major cloud providers, as well as an array of on-premise storage solutions. And as with any other piece of infrastructure, Kubernetes abstracts the details of the storage device. And it provides a uniform way of accessing that storage independent of the specifics of the storage device. So for instance, both block devices and file system storage are exposed as mounted file system volumes that are available to the application container. So the focus right now for the next few slides is on block and on file. But later we will also discuss other ways of consuming storage for stateful applications, including row block devices, as well as using cloud-native databases. Any questions? All right. So while there are many different ways of consuming storage in Kubernetes, we're going to focus on dynamic storage provisioning for persistent storage. And we care about persistent storage because that's really what it's needed to run stateful applications. And we only talk about dynamic storage provisioning because this is the recommended way of deploying storage in a cluster. It has a bunch of benefits, both for the users and for the users of the infrastructure, as well as for the administrators. First of all, it is self-service. So the administrator comes along and provisions the storage for the cluster. And after that, it does this once, and after that, it's completely out of the loop. Then, when an application requires the storage, it simply specifies what the storage requirements for that application are, and the administrator at that point is completely out of the loop. If you think about it, really, this is the only way. This is the only sane way of scaling storage provisioning in a cluster. So imagine if you have a cluster with 500 nodes, a bunch of storage arrays and so on, and applications coming and going, you really want this to be self-service. It is portable. As we mentioned before, application definitions make no direct references to the specifics of the storage device. And what this means is that then you can take an application description and run it in one cluster, and then take that same application and run it in a different cluster. And it doesn't matter if you were using, say, a cloud provider block device in one of the clusters, and you were using an on-prem array in the other cluster, right? And the other advantage is that it is on demand. So the storage for an application, it's actually provisioned at the time of use. What this means is that when you deploy the application in the cluster, this is when the storage is provisioned, not before. And again, the sysadmin does not need to be involved in the process. So let's look in a little more detail on how the storage is used by an application. So in Kubernetes, every piece of infrastructure is represented as a Kubernetes object. Right? And so, for example, if you have the nodes that Niraj showed in the previous slide, they are represented as in the API server inside the master as an object that maps to that particular node. The storage is no different in that sense. So there are also a number of objects and concepts that are in Kubernetes that are mapped to storage. So, for instance, a persistent volume is really, it's really a Kubernetes object that represents some piece of provision storage. It could be a cloud block device, or it could be our, an on-prem storage array, a partition on an on-prem storage array.
So you list the NFS, which is file-based, and the other is the block. What about object? An object like stores be a DB file?
So currently there is no way of directly exposing object as a storage device in in Kubernetes. Everything is, well, block or files, and there are some other options. If you guys were here for the previous talk for the Google talk, they talk about some of the other storage options. There is no standardized interface for objects, so that's also one of the reasons why it is not done yet. So going back to this, so in the case of persistent volumes, in the case of dynamic provisioning, which is what we're interested in, the persistent volumes are really created at the time of provisioning, not ahead of time. And so we'll see in a second how this happens, right? So how do we use that storage? How do applications use the storage? So in Kubernetes, the storage is used and requested via a persistent volume claim. And a persistent volume claim is yet another Kubernetes object that describes at a high level what are the requirements, the storage requirements for the application. So here we have a persistent volume claim named my claim, and it is requesting 8 gigabytes of storage for the application. Right? It also specifies a storage class SSD, and so storage classes allow admins to configure and make the storage available in the cluster, and then applications can reference that storage via that storage class name. In the case, and storage classes are also required for dynamic storage provisioning. So this is a core component of dynamic storage provisioning. We'll see that in a second. Okay, so we have our persistent volume claim, and let's see how we use that claim in an application. So we have a definition. Here we have a definition for an application. It's a stateful application, something I wrote. It's called my app, and it stores its data in a directory called data/myapp. And we want to make sure that it is persisted. If I shut down the pod and so on, then if it comes back, that it can read the data back. So what we're going to do is then we're going to say that this directory is backed by a volume. And so we're going to say, well, mount this volume, data volume, at this particular path, and I'm storing the data there, right? Now, the definition for that volume, it's backed by a persistent volume claim. Right? And so this is the same persistent volume claim that we defined before. Right? So, any questions so far? Okay, good. So let's see how it works all together. So we have our application definition, the one that I showed in the previous slide. We submit that to Kubernetes. Kubernetes decides to schedule this application in a node. Turns out that the application definition has a reference to a persistent volume claim. Okay, so Kubernetes sees this. It also says that the persistent volume claim references a storage class. With that, it selects which storage provider, a provisioner, will use to provision the storage. The storage provisioner will take the information from the storage class and the persistent volume claim and go ahead and talk to the storage device and provision the storage for the application. And so in this case, it could be mounting an NFS volume or creating a partition and making it available for use. Once the volume has been created, the provisioner will create a representation for that provision storage. So it will create a persistent volume. Kubernetes will then go and bind the persistent volume claim with the persistent volume. Once this happens, then the volume is ready to be used within a container. So at that point, then the volume is mounted in the container for the app, and the app can go and write to it. Okay. So As we mentioned earlier in the previous slides, Kubernetes already has support for many different storage providers. And as you saw in the Google Folks talk, the support for new storage providers will be done via the Container Storage Interface, or CSI. And so CSI defines a standard interface for container orchestrators, so they can expose arbitrary storage systems, and it also works with other orchestrator systems, not just Kubernetes. And so if you, for additional details, please refer either to their talk or to the CSI spec. Okay. So as we can see, Kubernetes already provides a simple-to-use uniform abstraction to use persistent storage in our applications. So, and what this means, it has enabled really rapid adoption of Kubernetes as a platform for deploying stateful applications. Now, when we're running these stateful applications in production, really, it is not enough to just persist the data. We have other concerns around resiliency and data management. So, as people in the audience have pointed out, we really want to create and manage backups for disaster recovery. We may want to migrate our data, not just our data, our applications from one cluster to another, right? So products like Kasten's K10 actually help managing the lifecycle of the application. It allows moving entire applications entire stateful applications with their data from one cluster to another, independent of what storage provider you're using. And as Niraj mentioned at the beginning, this is really not a vendor talk, so this is as much as I'm going to talk about it. But if you guys are interested in finding out more details, please come talk to us offline after the talk, or look us up online at kasten.io. Any questions? All right. If there are no questions, I'll hand it back to Niraj.
Thanks, Julio. Okay, so we're going to switch tracks a little bit at this point in time, right? We talked about storage infrastructure, we talked about vendor support, some of the underlying plumbing that Kubernetes uses to provision storage up to applications. But I think, especially for this community, it's very useful to see how this is being used, how people are consuming it, right? How things are shifted, how potentially some vendors are being commoditized. So it's good to think about some of the higher level concepts that will make things successful. When you go back in history, when Kubernetes first originated roughly 3 years ago, or a little less than that at this point, it was very successful for stateless applications. And it's not just because it was a container scheduler, but because it had concepts built in that supported building stateless applications and made it much simpler. And over the course of the last 12 to 18 months or so, we've seen similar concepts show up on the stateful side of things too. And it's good to think about that. Some of that are concerned with building applications. Some of it maps to how we manage these applications in an automated manner. And so we're going to spend a little bit of time talking about those things now. In particular, we're going to first talk about this concept called StatefulSets. Right? It's a Kubernetes concept, but it's really built for stateful applications that have more requirements than a stateless one. In particular, it'll give every component of an app, say for example, you have a replication cluster from MongoDB or Zookeeper, a stable ID, where no matter where your app gets scheduled, no matter if it gets rescheduled, restarted on a different node altogether, it always retains the same DNS name. So people can find each other in the cluster you might have set up. So obviously stable persistence, so you have a static mapping between identified pod or container versus its storage that is used across restarts, reschedules. So support for ordered operation. So when you bring an application up for the first time, when you upgrade it, when you go and maybe scale it down, scale it up. If there are specific things you need to do in order to maintain your quorum, it gives you support for that. And so this is powerful, so you have less work to do at your application layer when you deploy apps using the stateful set concept today. But more than stateful sets, the course of, you'll sometimes hear a lot about the operator design pattern. This is how people are adopting new patterns to deploy and manage these stateful applications running in this environment. At a very high level, the goal is to convert all the human operator knowledge, whether it be part of manual playbooks or otherwise, and codify that into software. It's built around a simple control loop. You'll see this again show up in the literature that observes the state of the system, and analyzes it versus what desired state might be. Say, for example, you say, I need 5 replicas of something, you only have 3. It'll act on that to bring it up to whatever your desired state is, and this can be very powerful there. So it can be used for supporting complex operations in your stateful app, such as backups, recoveries, scaling up and down. There's the active reconciliation we just talked about. And because people are doing this for a variety of different applications, there are a lot of SDKs out there that help you concentrate on your business logic instead of worrying about all the API machinery to watch for changes in the environment, to watch for changes in the application. Still a few rough edges there, but the community is doing a lot of work in that, so it's definitely usable. We ourselves do it, so do a lot of other people we know. And it's very extensible using native concepts, so you aren't using different tools, different management stacks. All of it props out of the same Kubernetes API you get used to when running these platforms. Now we're going to spend a little bit of time on the operator design pattern to dive a little bit deeper into it. And we're going to pick a particular project that we are developing in the open source called Kanister. It's built for managing stateful applications at scale. There are public examples on GitHub for some of the logos you see out there. But it's really how do you separate mechanism for policy and how do you run common operations such as data backup and recovery or data migration, data masking, things of that nature that are very critical in some of these environments as people are running multiple clusters, test dev clusters, you need to move data around. So how does all of that work is what we do in Kanister. But this is not a Kanister talk, but I'm going to use Kanister to illustrate how the operator pattern works and use examples from that. So at the very high level, when you look at operators, the concepts are relatively simple. You have an application you've deployed, could be 1 or more containers. You want to do something to this application, right? Either scale it up, scale it down, upgrade. Maybe you want to take a backup of the data in it, mask data, no matter what it might be. So there's an action that you specify. And as Julio mentioned, everything is specified using a Kubernetes object. And then you have a controller that sits off on the side that monitors changes either to the application or new requests come up that perturb the state of the application and will react to that. Yeah. So that's at the high level, the operator pattern. Any questions on this before we make it a little bit more concrete? No? Okay. So we're going to use Kanister, but more than that, we're going to use Postgres as an application here, right? So we have Postgres running, we have object storage. While there was a question about object storage abstractions earlier, even though there is no common abstraction, we see a lot of object storage used in Kubernetes environments today. And we have the controller I showed on the last slide. Let's say we want to do something to it. In this particular example, I'm going to use backup as an action. I want to extract the data from Postgres for failure, for masking, no matter what it might be. And so we do that by creating a custom Kubernetes object in the namespace. The controller has been watching for changes to these two things. And so when this shows up, it says, I have work to do. And it will go and run stuff in the context of your application. Right? There is a question about how it knows what it means to do Postgres backups as an example. So we're not just doing storage level backups, even though that's an option in Kanister too. But let's say you want to do something particular to Postgres. And for that, in the Kanister system, we actually have blueprints that sit off on the side. Some people codify everything in controllers usually as part of Go. We made it very extensible. So you want to write bash scripts, Python, or Go code. Everything just plugs into it. But based on what your custom needs are on Postgres, you will go do stuff. In this particular example, we just back data up. So we ship a base backup and any logs we might need to do point-in-time restore into an object storage system. Right? Now, this is somewhat of a complicated case, but the same mechanism could be used to take a volume level snapshot underneath this as an example, quiesce the application. So the flexible blueprints that we'll look at as to how that works. So, and once all of that is done, you go update the application. You say, hey, my desired state of the world is now matching what my actual state of the world is, whether it be scaling up the application, adding a replica, or in this case, doing a backup. Yep. So in the next couple of slides, just going to briefly touch upon what these custom objects look like, what a blueprint looks like to modify your stateful applications. But any questions on what we've seen so far? All right. So an action, in this case, we just call this an action set, right? All Kubernetes presentations, as you've noticed, will have YAML. So we are doing the same thing here too. It simply, it specifies an API version and it says, hey, this is a kind of action set. And all it tells the system to do, or the controller that's watching it, is run this action, which is of type backup. We do have a couple of different things in there. We'll say, hey, use the Postgres blueprint I might have defined. I might have custom extensions in there. run it against the stateful set Postgres was deployed under in this namespace. I could have multiple Postgres instances running. People run a lot of that in common. And potentially other configuration you might need to feed it that's particular to the state of your system out there. Yep. So this is all you need when we talk about these custom resources. When people talk about custom resources in Kubernetes, I'll think of it basically as some form of YAML that someone understands, has a schema for it. Okay? It's actually simple to think and reason about there. And now when we look at the blueprint that we referenced in here, it's something, again, that you create, yet another Kubernetes object, so everything's Kubernetes native there, where it has particular actions. But just in this case, because this is shared across different clusters, we specify what it means to do a backup here. In this case, we say, hey, there's some templating in there, ignore that for a second. But it's really saying within the context of the application, potentially in a container, run a tool. In this case, we run no Postgres-specific tool. You can have other phases as a part of your pipeline where first phase maybe extracts data from Postgres. The second phase might encrypt it before you push it off to another object store. Just there. And you can have other actions. You can define whatever's custom to your environment, mask data, restore, things of that nature. Yep. So kanister this is how some of that works within the context of the operator pattern. It's in somewhat of an Uber operator. It can handle multiple data services, especially if you're running polyglot persistence in your stack, which is what we see over and over again in our customer deployments out there. But it's not just us running things, right? There are stateful applications in this, there's a list of this project called Awesome Operators, including most of your commonly used data services out there, right? So go check it out and you will run into examples and a lot of these are now also being supplied by vendors out there. Yep. So that's about operators, the design pattern there. You'll see more and more of that show up. In fact, storage systems such as Rook themselves internally use this to manage the stateful storage clusters. So it is actually quite extensible, quite powerful. So we've talked about how to deploy and manage, how to manage a lot of these applications at runtime. But when you're in these environments, it's also good to think about how you're going to package and deploy these things, right? There are multiple ways to deploy applications in Kubernetes today. If you're not familiar with it, if you aren't using Helm already, we definitely recommend you go look at that and use it. As with a number of things Kubernetes, it has a nautical team. But at the very high level, think of Helm as your package manager. It's your apt-get or yum that you'll see in Linux. From the context of this presentation, it makes it very easy for you to get up and running with stateful apps. Right? So to go run Postgres on your cluster is a single line command. You simply do a Helm install, pick the stable chart that's called Postgres, and you're off to the races. It'll bring things up for you. Or you run MongoDB cluster, it'll bring up a replicated Mongo cluster for you. So it's a good place to get started with some of these things. It's also a good place for when you start configuring this, right? When you need to organize settings. Instead of convoluted setups, you can specify options to your Helm chart. Say, I want more storage. I want to use a different storage class that Julio talked about earlier. So it's easy to plug and play a lot of these things using common concepts. And when finally building out your applications, it also supports composability. It's easy to include external charts or other internal charts into your app. Say you're building something that depends on Couchbase. Just pull in a reference to that and you're done. Right? So you don't need to worry about how that's set up. Some of your settings can flow through to that too. So it's powerful in doing some of that too. Generally, what people use is they take a lot of the stateful charts as a jumping off point and modify it for the custom needs, but a lot of them will just work off the shelf for you too. Yeah. Questions on Helm? Right. So again, going to switch tracks now a little bit. Going to focus a little bit more on the future. Some of these things are stuff that is still in development in the community, but it is worth checking out, worth keeping an eye out on. And so we'll talk about two of those things here. The first one being cloud-native databases. Right? So if you remember the very beginning of the presentation, we talked about some of the philosophies that have gone into Kubernetes. But stateful applications are building this into their systems themselves so that they become much easier to use and much more powerful in terms of building applications on top of it. Examples of these include cockroachdb, vitess, yugabyte, etc. And all of these are built to be very large data stores, right? Large number of terabytes of data in it, a lot of load. So they're built upfront to be scalable there. They assume failures are a fact of life. Failures will happen often in these systems, so they're built to be highly resilient. And things that used to be scary back in the day, hey, how do I fail over? What are the storage implications of that? What does it mean to fail over from primary to secondary? they happen transparently to any consuming application. So it's easier to build highly available applications on top of some of these platforms. They also self-manage more than some of the other systems, right? And there's obviously, right, there's a promise in the claims versus what exists today, but they will do stuff in terms of auto rebalancing in response to load, in response to your data sizes growing. So you're on a priori deciding, hey, these are the buckets in my database cluster, and this is how I'm going to do sharding. Some of it would happen naturally for you as your workload characteristics change. So definitely something to keep an eye out on as these systems mature, as more stuff happens in this space out there too. And for some of the people in this room, right, most of what this talk today has been about has been shared persistent storage. But as one would imagine, there's a lot of ask to use local storage in these systems too. So whether it be local spinning disks, magnetic disks, when you think about systems like Cassandra, which really don't like SANs, any form of shared storage, because they want to control their own replication, storage systems like OpenEBS or Ceph. So all of these systems want to go leverage local disks. And so there's a feature in Kubernetes called local persistent volumes. It's currently in beta. The advantages of it is, again, uses common primitives that we've talked about, persistent volumes, volume claims, storage classes. So if you have a pre-existing application and you know what you're doing, you want to point it to local storage, all you do is just change the storage class. If it was a Helm chart, just one parameter gets you up and running with using local storage, whether it be for better performance, test dev, whatever it might be. A lot better scheduling in terms of other features that came before it. Kubernetes has this feature called host path. Don't use it. Trust me on that one, unless you really, really know what you're doing. So, but local persistent volumes has much better scheduling for pods. Local storage has pod affinity. It'll kick other things out to make sure the right thing happens there. And more recently, something that was subtle in this and other presentations, in most cases, when you talk about even exposing block storage to containers within Kubernetes, it is almost always exposed as a formatted file system. But we now have the ability to expose that as raw block too, if that is what you really, really want to do and munge and manage bits individually. That is now a potential and possibility in these systems today. Yep. So finally, right, to wrap up here, right, we talked about how Kubernetes has become a lot more ready for production stateful workloads today. We covered a number of different topics in this area. We talked about platform support, not just from some of the abstraction primitives that help people, but also from the purposes of the top level features that make application level easier. There's a lot of storage vendor choice out there, right? The talk before me, the multiple options on-prem and public clouds. There's a number of relational and NoSQL systems that both supported as a first-class citizen. There's a cloud-native database work that's also happening in that space. And finally, we didn't talk about it in this talk, but it's not just, hey, trust Niraj, he tells you it's ready, go use it. But a lot of independent surveys have also started to show this information. Sysdig had a survey, SIGAPS ran a survey earlier this year where people that responded to the survey and were running Kubernetes, over 50% of them were running some NoSQL system or a relational database. If you count things like message queues, that number even goes up higher than that. So there's a lot of people using it out there today in multiple styles of environments. Yeah. So this is all I have to talk about today. Happy to take any other questions. We have roughly 10 minutes before the next speaker needs to come up and get ready. But we can talk about anything under the sun that interests you. Go ahead.
With regards to dynamic provisioning, is there any means where your persistent volume would get deleted, or does eventually the storage admin have to come in and do garbage collection if apps become obsolete or whatever?
It's a great question. So there is a life cycle in this. Let me see if I have a slide on this somewhere. Give me one sec. Yeah. So, right, there is this. When you look at a storage volume within Kubernetes today, it goes through this. You provision it. Could be dynamic, could be static. Really use dynamic provisioning. Julio talked about the bind use case. Once it's provisioned, your app is up, binding those two things together, you mount it, and you start using it. Okay? Then it depends on what you've actually set. And some of this is also editable at runtime. When you've created your app, you say, what is my retention policy? Right? Do I delete when the app goes away and I'm going to asterisk that? Or do I retain it forever? And that is up to folks. The delete is not about, hey, if my process restarts, if my node dies, the volume will disappear. No, if it's explicit command to go delete that application, only then does your volume get deprovisioned, so as to speak. Okay. Otherwise, it can get retained, but that is up to our choice. Now, there's always potential for accidental misuse of that. And so for that, again, there are techniques in place where you can assign quotas to storage classes, whether it be in terms of number of volumes or capacity of volumes. So if you're doing stuff and you're littering and leaking, generally you'll run into this quota limitations, and then you go find out, hey, do I need more quota, or is it just, right, someone set this wrong retention policy and I just litter all over the place. Okay? So we didn't cover all the flavors of local disk today, right? I just covered one, which is a recommended path forward. But for all practical purposes, there are 3 different flavors. There is empty dir, which is scratch space. If your container even gets restarted somewhere else, it's gone, definitely. No promises made whatsoever. There is host path, which again, right, maybe your data resides on some other node, but you got rescheduled somewhere else, so you're starting off from scratch. But Kubernetes is not a storage subsystem. Okay, so it does not manipulate data. It will not move data around for you. Right? There is some stuff that, for example, we do at Kasten in terms of high-level data management, but depending on what the problem is, there are other solutions. But really, local storage, short of using local persistent volumes, this feature, but even with this, there's no one moving data around for you. All right. Thank you very much. Right, the slides available online. You can get them from SDC, email us, right, if you have any other questions. And right, we'd love to talk to all of you. Thank you.